It started quietly. No breaking news, no emergency press conference. Just a faint smudge of light in Virgo, caught by an amateur astrophotographer in Tuscany. GO 431 UTC November 11th, 2025. At first, it looked like nothing. A fuzzy object, magnitude +112, nearly lost in the morning haze before sunrise. But the coordinates matched something that should have been gone forever. 3I Atlas. The third confirmed interstellar visitor in human history, discovered by NASA's Atlas telescope in Chile on July 1st, 2025. It had already raced past the sun, slipped behind the solar glare, and was expected to vanish into the darkness between stars, a ghost fading beyond reach. Yet here it was again. For astronomers, that changed everything. The comet's reappearance wasn't supposed to be possible. Interstellar trajectories are hyperbolic, one-way tickets. When 1I Oumuamua passed through in 2017, it accelerated away at 26 km/s and never returned. 2I Borisov followed in 2019, leaving behind a perfect trail of cyanide and carbon dust. But 3I Atlas, the fossil of time, as researchers called it, had somehow slowed down. Its apparent motion across the sky didn't match predictions from JPL's Horizons database or ESA's Solar System Dynamics models. Something had changed. In late August, the Gemini South Observatory in Chile recorded high-resolution spectra showing metallic signatures, iron and nickel ratios inconsistent with solar system comets. Then came a strange note from the Sphere X mission team, an increase in mid-infrared reflectivity at perihelion, suggesting renewed outgassing months after peak heating. That shouldn't happen. Comets fade. They don't restart. By September, 3I Atlas was out of view, hidden behind the sun. NASA's solar observatories, SOHO, Stereo A, Parker Solar Probe, were too busy with the October solar storm series to maintain steady coverage. Then came the silence. NASA's Deep Space Network dropped its Atlas data feed for 3 weeks during the government shutdown. The public dashboard froze. When signals resumed, the data log jumped. A gap, no trajectory update. And now, in November, the comet was visible again, this time brighter and with multiple tails. The Virtual Telescope project in Italy confirmed it. 3 distinct plumes streaming from a single nucleus, plus a narrow spike opposite the sun, an anti-tail. Images from Gianluca Massi's RTEC 250 astrograph showed a rotation in dust jets, as if something deep inside the nucleus had reawakened. How? Why now? And what could reignite a 7-billion-year-old relic from another star? The data from Gemini North hinted at the impossible. Thermal activity correlated with changes in spin rate. It looked as if the comet had briefly stabilized, as though responding to an internal pulse. Of course, scientists stayed cautious. Every anomaly demands an explanation grounded in physics, sublimation cycles, refractory ices, micrometeoroid impacts. Still, the timing felt strange. By December 19, 2025, 3I Atlas would make its closest pass to Earth, 0.0018 AU farther than Mars's average orbit, roughly 270 million kilometers away. Too far for naked eye viewing, but close enough for instruments to listen, because maybe, just maybe, the interstellar traveler wasn't quite done speaking. Here's what we know. 3I Atlas is an interstellar comet, likely 7 billion years old, with a metallic composition unlike any local body. It reappeared unexpectedly in November 2025, showing unusual brightness and multiple dust tails. Here's what we don't. Why its outgassing resumed months after perihelion. Why its rotation and trajectory slightly deviate from models. And whether this reactivation signals a natural process or something no comet has ever done before. In science, surprises are meant to fade under data. But this one didn't. By late November 2025, observatories across both hemispheres were racing to track the revived 3I Atlas. The Gemini North Telescope in Hawaii switched from time-domain spectroscopy to rapid imaging. The European Southern Observatory authorized emergency observing hours on the Very Large Telescope at Cerro Paranal. Even amateur astronomers joined in. Remote networks from Chile to Spain were uploading nightly stacks to the Minor Planet Center. And all of them noticed the same thing: the comet was flickering. Not in brightness, but in spectrum. The reflected light curve showed faint, rhythmic modulations every 14.6 hours. At first, that suggested a rotation period, common for small bodies. But when researchers corrected for dust coma interference, a secondary modulation appeared, offset by 47 minutes. 2 overlapping signals. That was odd. 3I Atlas wasn't behaving like a single tumbling fragment. It looked like a binary nucleus, possibly 2 cores locked in a slow mutual orbit. Yet high-resolution imagery from Gemini South and the Hubble Wide Field Camera, taken July 21, 2025, had shown only one condensed nucleus. So where had the second one come from? NASA's Planetary Science Division released a cautious memo on December 2nd. Observed spectral duality may indicate internal fragmentation. Continued monitoring is advised until peri-Earth passage. But the memo didn't address the other mystery: the spectral echoes. Buried in the high-resolution data was a repeating pattern at 3.9 microns, an absorption dip that mirrored the spectral fingerprint of silicate dust from protoplanetary disks. In other words, material older than our Sun. How did they know? Because that signature, magnesium iron silicate in amorphous form, had only been observed in infrared data from the James Webb Space Telescope in young systems like HL Tauri and Beta Pictoris. And now it was shining back from 3I Atlas. If verified, it meant this object had formed around a star that lived and died long before the Sun's birth. It was, quite literally, a messenger from a vanished world. The press called it the fossil of another dawn. NASA, more cautiously, labeled it anomalous inheritance. Meanwhile, the comet kept changing. Its tail split again, 5 strands now, fanning like the ribs of a cosmic fan. Polarimetric data from the Lowell Observatory showed an increase in negative polarization beyond 4%, a value unmatched in any known comet. That implied unusual grain alignment. Maybe magnetic, maybe electrostatic. ESA's ExoMars Trace Gas Orbiter, still orbiting the red planet, captured a glimpse on October 3rd, while the comet was behind the Sun from Earth's view. The onboard CASSIAS camera tracked it against streaked star fields. The image was noisy, but there was motion, as if jets pulsed from beneath the crust. Some models suggested volatile pockets being heated from within, not the surface. That's not standard physics. Comets heat from the outside. So, again, what was happening inside 3I Atlas? When the data reached Caltech's Infrared Processing Center, an unexpected line appeared in the preliminary model notes: energy redistribution inconsistent with passive thermal conduction. In plain English, heat seemed to be moving too efficiently. Either the nucleus contained channels, hollow tunnels of sublimated ice, or something denser was conducting heat deep below. Iron-nickel alloys could do that, but metallic cores in comets? That was unheard of. By early December, the object brightened another half magnitude, hovering around plus on 11.4. Not enough for human eyes, but enough for the network of C-star and dwarf smart telescopes to begin capturing it automatically. For the first time, the public could witness the visitor. A streak across Virgo, tiny, ghostly, and ancient beyond comprehension. Here's what we know. 3I Atlas shows dual rotational signals, likely caused by internal fragmentation or binary behavior. Its spectrum contains silicate dust consistent with presolar material, and its thermal profile suggests non-standard heat conduction. Here's what we don't: whether the object's structure truly includes metallic components, why it reignited from within, or how an interstellar comet could retain internal volatiles after billions of years in deep space. Science advances by continuity. Observation leads to measurement. Measurement leads to pattern. Pattern leads to truth. But every once in a while something interrupts that chain. A gap so small it's dismissed at first, then impossible to ignore. That gap began on October 1st, 2025, the first day of the US federal shutdown. NASA's internal communication network went into data preservation mode. Non-critical systems, including the Asteroid Terrestrial Impact Last Alert System, ATLAS, stopped uploading to the public archive. That alone wasn't unusual. But 3 weeks later, when access was restored, researchers noticed something strange. Between October 3rd and October 24th, no raw data packets existed from Atlas, Chile. The telescope's automated logs had restarted, but the timestamps jumped forward 21 days with no recorded downtime, no calibration files, no dark frames, no exposure metadata. As if the observatory had never paused at all. When a group at the University of Arizona's Lunar and Planetary Laboratory requested the missing data through the Planetary Data System, they received a short reply. Archive synchronization completed. No anomalies detected. But the anomalies were there, just not where anyone expected them. During those same 21 days, Mars-based sensors were still recording. ESA's ExoMars Trace Gas Orbiter and NASA's Mars Reconnaissance Orbiter had both caught unregistered emissions near the coordinates corresponding to 3I Atlas's predicted solar conjunction path. CASS images showed a faint, fast-moving object whose coma fluctuated in intensity over 36 hours. A pulsing effect. At first, astronomers suspected image processing artifacts, but when the Hubble Space Telescope resumed tracking in late October, the comet's surface albedo had jumped by nearly 18% compared to its pre-perihelion phase. Comets don't do that, not after solar heating should have stripped their volatile surfaces bare. Was something replenishing the surface, or had a deeper layer become exposed, one shielded for billions of years? To understand that, teams turned to spectroscopy. Gemini North's GMOS instrument detected a new emission line around 470 nanometers, corresponding to molecular nickel gas, incredibly rare for a comet. In ordinary solar system bodies, nickel sublimates only at extreme temperatures, near 1450 degrees C. For 3I Atlas, with a perihelion distance of 0.64 AU, that heat shouldn't exist, unless something else was driving it. In December 2025, Dr. Keiko Mizushima of Kyoto University presented a preprint paper suggesting endogenic heating. Internal warming triggered by rapid crystallization of amorphous ice pockets. When certain ices restructure, they release latent heat. That process can cascade like a slow internal explosion. Her model explained the observed reactivation and tail bifurcation, but it failed to explain the timing, why the heat surge coincided exactly with the missing data window. The coincidence was too neat for comfort. On October 3rd, the day the Atlas data stream cut off, the ExoMars CASS camera captured its first glowing frame of the comet. By October 24th, when NASA's feed resumed, the brightness spike had stabilized. 3 weeks of silence, 3 weeks of transformation. When 3I Atlas reappeared to Earth's telescopes, it was different. Its coma density had increased threefold. Spectral scans showed a higher carbon dioxide to water ratio, 1:3.1, instead of the usual 0.5.1 for typical comets. Dust jets rotated more slowly, implying a shift in torque balance. And, most surprisingly, the object's non-gravitational acceleration had flipped sign. Instead of decelerating outward, it was nudging inward towards the Sun by 4.8 5 ms2. Tiny, yes, but enough to alter its projected exit trajectory by 6,000 kilometers, an unheard-of variance for a body with no propulsion. JPL engineers recalculated the hyperbolic excess velocity at 27.1 km/s, down from the original 28.0. A mere 0.9 km/s difference, yet statistically impossible without sustained mass loss in a specific direction. And the direction? Almost perfectly radial, aligned with the Sun. To any mission planner, that looked like thrust. To scientists, it looked like physics behaving badly. The official line, issued by NASA's Planetary Defense Coordination Office, was cautious. Observed acceleration likely results from asymmetric outgassing. No evidence of artificial influence. But several independent astronomers, including Dr. Thomas Greaves of the Royal Astronomical Society, noted something subtle in the JPL trajectory charts. The change began not when the comet neared the Sun, but precisely when Earth lost visual contact. That raised a simple, uncomfortable question. What happened to 3I Atlas while no one was watching? Here's what we know. Between October 3, 2025, 3I Atlas underwent a transformation unseen by Earth-based instruments, an increase in brightness, a rise in surface reflectivity, new molecular emissions, and a reversal in its non-gravitational acceleration vector. Here's what we don't: why those changes occurred exactly during a period of lost data, whether endogenic heating alone can explain the behavior, or if the comet interacted with something near perihelion that altered its structure, trajectory, and energy balance. By December 10, 2025, the northern skies before dawn were filled with quiet excitement. The faint smudge, once visible only to high-powered telescopes, was now being tracked by dozens of amateur observatories across Europe and Asia. Images stacked from Japan's Tenegra Deep Sky Array showed something scientists had begun whispering about privately: a thermal inversion. Normally, as a comet moves away from the Sun, it cools, its outgassing slows, its coma fades. But the thermal readings from 3I Atlas, captured by NASA's NEOWISE and SphereX missions, showed the opposite. It was getting hotter. Infrared fluxes in the 4.55 mm band rose by 22% between November 28th and December 7th, even though the comet was receding from the Sun at 38 km/s. Dust emission didn't match the energy input. The sublimation curve, the chart every comet modeler uses to predict activity, had inverted. Dr. Lea Moretti from the Italian National Institute for Astrophysics said it bluntly in her weekly summary: either our instruments are wrong or something unprecedented is happening inside that nucleus. So what could cause a comet to warm up as it moved away from its heat source? One hypothesis pointed to phase transitions, buried ices of methane, ammonia, or carbon dioxide changing structure and releasing trapped heat. Another model, proposed by the Jet Propulsion Laboratory's Thermal Dynamics team, introduced piezoelectric heating, mechanical stress within crystalline ice generating small electric discharges as the comet flexed during rotation. That would require internal structures, fractures, voids, even conductive veins of metal-bearing ice, acting as filaments. And that word, metallic, returned to the conversation, because by now 3I Atlas was producing strong nickel and iron vapor lines in its spectra, something that required sustained temperatures exceeding 1000 degrees Celsius. Yet the outer surface averaged no more than 62 degrees. The contradiction became known internally at NASA as the thermal paradox. When the Gemini North Telescope captured a set of polarization images on December 9th, they revealed faint, evenly spaced arcs within the coma, almost like wavefronts. Each arc represented a release of dust and gas, pulsed approximately every 7 hours. That matched the secondary rotation period first identified in November, the inner beat superimposed on the 14-hour primary spin. It was as if the comet's two halves were breathing in rhythm, exchanging bursts of thermal energy through some hidden channel. Moretti's team at INF ran simulations using the Thermodust 3.2 model. Their results suggested localized heating traveling through subcrustal tunnels, conduits roughly 40 to 100 meters wide. If true, it meant the object had hollow passages, a feature never observed in natural comets. Such structures would require internal melting and refreezing over millions of years. An impossibility for a body wandering the interstellar void at 207 degrees Celsius. When asked for comment, ESA's Comet researcher Dr. Elodie Dufresne gave a weary smile. "We can't say it's unique because that assumes we've seen others like it. We haven't. 3I Atlas is teaching us how little we know about what happens beyond the sun's reach." Meanwhile, the object's photometric profile kept changing. By mid-December, as it climbed toward the constellation Leo, the coma's color index shifted from PL 0.8, typical gray, to PL 0.3, a colder, bluer hue. That implied the dust grains were becoming finer, more reflective, possibly freshly ejected material from inside. It was shedding its ancient outer layer, revealing something newer beneath. The temperature maps from Sphere X gave the same message. Heat wasn't radiating out. It was moving across, distributed almost evenly across the nucleus. That suggested internal convection or a dense metallic network capable of transferring energy laterally. In other words, a self-regulating system. To most astronomers, that was unthinkable. To some, it was thrilling. A body that had survived interstellar radiation for billions of years shouldn't behave like a dynamic engine. But 3I Atlas was rewriting comet physics in real time. Still, as the data accumulated, one question loomed larger. If this heat was being generated from within, where did the energy come from? There was no fusion, no tidal friction, no radioactive decay strong enough to explain it. Only one source remained plausible: the slow collapse of trapped volatile cavities under internal stress, a final outburst from a frozen heart. A cosmic dying breath. A flare from a traveler who had journeyed too long between the stars. Here's what we know. 3I Atlas is displaying internal heating, inconsistent with standard comet models. Thermal flux is rising despite increasing distance from the sun. Nickel and iron vapor lines suggest temperatures near 1000 degrees, likely driven by internal phase transitions or mechanical stress. Here's what we don't: what mechanism transfers heat across the nucleus so efficiently, why activity is pulsed in synchronized cycles, and whether these signals mark a final disintegration or a deeper, unknown process preserved since another star's dawn. By December 14, 2025, the narrative surrounding 3I Atlas had split into two worlds. In public, it was a scientific marvel, an ancient relic from another system, visible through telescopes before sunrise. In private Slack channels and encrypted research threads, however, astronomers and planetary scientists were quietly confronting data that made no sense. The comet was not disintegrating, it was reorganizing. New data from the Gemini South Multi-Object Spectrograph, GMOS, revealed that the dust jets were not random. They emerged from specific coordinates on the nucleus, maintaining angular separations of 60 degrees, forming a perfect hexagonal symmetry over multiple rotations. Natural fractures don't do that. The team at the European Space Operations Center, ESOC, compared the dust pattern to simulations of stress distribution maps. Their conclusion: the emission points followed a lattice-like geometry, as if internal pressure was releasing through predefined structural paths. They called it the blueprint. That term stuck. On December 12th, the Hubble Space Telescope captured a composite image using its Wide Field Camera 3. By subtracting the background coma and stacking multiple exposures, a faint, linear shadow became visible across the nucleus, a groove or trench nearly 700 meters long. It ran parallel to the jet orientation. When NASA's analysis arrived 2 days later, it added another shock. Magnetic readings from the Parker Solar Probe, taken during its November perihelion sweep, registered a minor but measurable flux deviation, a dip of 0.3 nt, consistent with the passage of ionized dust interacting with the solar wind. In simple terms, the comet's expelled particles were carrying charge. That charge aligned along the same axis as the 6 emission jets. Coincidence? Perhaps. But the geometry was elegant, almost engineered. And scientists are wary of elegance in chaos. Dr. Jean-Marc Leclerc from the Paris Observatory tried to temper the excitement. Pattern does not mean design. Repetition is how physics speaks when we are too surprised to listen. Still, the phrase blueprint beneath the ice began appearing in internal memos. The next set of data came from the Infrared Telescope Facility, IRTF, on Mauna Kea. Spectroscopy showed transient spikes in CO2 emissions every 7 hours, matching the pulsation period observed earlier. The team overlaid the thermal and emission data, and the two datasets aligned perfectly. Each thermal pulse corresponded to a burst of ionized dust along the same magnetic axis. That should have been impossible for a tumbling, irregular comet, yet 3I Atlas seemed to have internal feedback, a cycle of pressure, release, and stabilization. The working theory evolved again. Maybe 3I Atlas wasn't solid at all. Maybe it was a porous lattice, a honeycomb of cavities, voids, and frozen bridges, remnants of its formation around a long-dead star. If that star had been more massive than the Sun, its system could have contained heavy elements, iron, nickel, cobalt, which condensed differently during the birth of planetary disks. Over billions of years, gravitational ejection could have flung one of those composite bodies into the interstellar medium. That body, after wandering for eons, could have retained metallic inclusions that allowed heat to move and energy to flow in unexpected ways. But one line of thought unsettled even the most pragmatic researchers. What if this wasn't the first time such a structure had passed near our Sun? Had other interstellar relics come and gone, unnoticed, faint, their signatures lost in centuries of unrecorded sky? In a late-night briefing streamed between JPL and ESA, Dr. Moretti summarized the growing unease. We keep treating it like a visitor. But maybe it's a messenger, not because it carries meaning, but because it embodies memory, a record of how matter once arranged itself under another sun. She paused, then added softly, "If this lattice is real, it could show us how solar systems die." The temperature curve from Spherex continued to rise. By December 16th, internal hotspots reached 1180 degrees according to radiometric modeling, enough to vaporize silicates. Still, the comet remained intact. It was venting, not breaking, releasing energy in controlled waves, preserving its core shape. That stability baffled dynamicists. Comets from our system crumble under 1/10 that stress. Yet this one, forged before Earth existed, held its form. And in that endurance, scientists saw something profound. Maybe stability wasn't the absence of chaos. Maybe it was the memory of survival, frozen into geometry. Here's what we know. 3I Atlas's outgassing follows a consistent hexagonal pattern, indicating internal organization or lattice-like stress channels. Charged dust aligns with magnetic fields, and periodic heating corresponds with synchronized emissions. Here's what we don't: whether the structure's precision is purely natural or the result of exotic material behavior formed around a different kind of star. We don't yet understand how such symmetry persists in a body billions of years old, or what happens when the lattice finally collapses. At first, it was just noise. Low-frequency static buried deep within magnetometer logs. A faint oscillation picked up by ESA's solar orbiter while scanning the heliospheric current sheet on December 18, 2025, 2 days before 3I Atlas reached its closest approach to Earth. The signal repeated every 7 hours and 3 minutes, the same period as the comet's internal thermal pulses. It wasn't radio communication, and no one suggested it was, but it was structured. The waveform contained a harmonic ladder, precise spacing between frequencies, unlike the random turbulence of solar plasma. At 0.004 Hz, the amplitude was small, but coherent. The Parker Solar Probe confirmed it independently 3 days later, a signature in the interplanetary magnetic field. A faint rhythmic modulation in phase with 3I Atlas's rotation. For scientists who had spent months studying its heat and dust, this was something new, sound without air, vibration without intent. They called it the Helios acoustic anomaly. When plotted against the comet's spin geometry, the peaks of this oscillation aligned with the release of charged dust jets along the hexagonal pattern discovered earlier. In other words, every time the comet exhaled, the magnetic field around it rippled ever so slightly, like a heartbeat in plasma. Dr. Keiko Mizushima, the thermal physicist from Kyoto, described it in one sentence that made its way through every science forum within hours. It's not a voice. It's the sound of stress leaving matter. Her team proposed that as the comet's lattice flexed, electrostatic discharges within metal-bearing ices were producing ultra-low frequency electromagnetic waves. Essentially, the comet was humming, a frozen relic of another star singing into the void. And humanity had instruments sensitive enough to hear it. By December 19th, 3I Atlas was at its closest approach, 270 million kilometers from Earth. Through the Gemini North, Lowell Observatory, and IRTF, observers captured the most detailed images ever recorded of an interstellar comet. Its coma now extended over 120,000 kilometers, and the anti-tail stretched backward toward the sun, a narrow spike glowing faintly green. Spectral data from NASA's SphereX and ESA's Bepi-Colombo, then near Mercury, confirmed unusual polar emissions. Ultraviolet flashes synchronized with the magnetic oscillations. The plasma tail wasn't just reacting to solar wind, it was modulating it. For comparison, typical comets produce stochastic, chaotic fluctuations. 3I Atlas was rhythmic, predictable. Each pulse followed a nearly perfect 7-hour interval. That was too clean to be coincidence. Still, the responsible teams refused to romanticize it. Every report emphasized natural mechanics, piezoelectric resonance, magnetic alignment, and stress propagation within metallic inclusions. Yet in their language, cautious, technical, understated, there was awe, because this song wasn't random interference. It was information, encoded not by intelligence, but by structure. A pattern preserved since before our sun ignited. Dr. Elodie Dufresne from ESA's Comet Physics Division summarized it during a live briefing. We are listening to crystallized time. Every oscillation carries the memory of another system's birth. Her words became the tagline of dozens of documentaries before the year ended. But behind the wonder, another discovery quietly unfolded. At the European Incoherent Scatter Scientific Association IceCat facility in Tromsø, Norway, radar backscatter experiments aimed at the comet detected faint echoes, delayed returns inconsistent with dust alone. The reflective cross-section fluctuated cyclically, suggesting interference from large-scale conductive surfaces, perhaps sheets or networks beneath the coma. If correct, those reflections could map the geometry of the internal lattice itself. A frozen web of metal and rock, humming under stress as it slowly vaporized. Meanwhile, the temperature continued its erratic climb. By December 21st, hotspots exceeded 1,300 degrees Celsius, while the overall body remained stable near 50 degrees Celsius. No fragmentation, no collapse. Instead, the pulses accelerated. 6 hours, then 5 hours and 55 minutes. The lattice was tightening. NASA's Deep Space Network recorded the final stable signal on December 22nd. After that, the electromagnetic oscillation vanished, absorbed by the widening plasma tail as 3I Atlas began its long departure into the dark. And just like that, the song stopped. Observers across the world watched as the interstellar traveler dimmed each morning, first a green shimmer near Regulus, then nothing but the cold blue of dawn. Astronomers called it the fading. Historians might one day call it the silence. Because for one brief moment, the oldest object humanity had ever observed didn't just reflect light, it vibrated, it resonated, it remembered. Here's what we know. 3I Atlas emitted low-frequency electromagnetic oscillations synchronized with thermal pulses and dust jets, forming a measurable magnetic modulation, the so-called Helios acoustic anomaly. Its internal lattice likely conducted these stresses through metallic channels. Here's what we don't. What sustained such resonance without structural failure? Why the frequency shortened before fading, and whether this phenomenon was unique to 3I Atlas, or a property shared by other interstellar relics still drifting unseen between the stars. By Christmas Eve 2025, the interstellar traveler had gone quiet. No light curves, no spectral lines, just the faint trace of its path, logged in terabytes of data stored across observatories from Chile to Mauna Kea. The song of 3I Atlas, that subtle, rhythmic pulse in the magnetic field, faded completely by December 22, 2025, 17 Maction UTC. NASA confirmed the loss of coherent signal in a bulletin that same evening. Object stable. Outbound trajectory nominal. No further emissions detected. To most of the world, that marked the end of the story. But to those who had listened closest, silence was not an ending. It was a recording. In early January 2026, researchers at the Max Planck Institute for Solar System Research began analyzing the residual data from Parker, Solar Orbiter, and ESCAT. When they overlapped the electromagnetic oscillations, the intervals formed a harmonic sequence. Not random, not noise. Each pulse drifted downward in frequency over time, forming a descending curve. The physical sign of energy release through structured decay. To the human ear, converted into audible range, it sounded almost like a sigh. The comet had not simply gone silent. It had completed a cycle. The first comprehensive post-mission report, 3I Atlas, a structural study of an interstellar cometary body, ran 618 pages. Its conclusions were cautious but extraordinary. 3I Atlas likely contained a metal silicate lattice, a crystalline network capable of distributing thermal and mechanical energy far more efficiently than porous ice. That network, formed around a metal-rich protostar roughly 7 billion years ago, had survived radiation, collisions, and the vacuum of interstellar space. When the comet entered our solar system, solar radiation triggered a cascade of phase transitions along that lattice, releasing heat and electromagnetic resonance, a physical melody written in stress and time. For decades, astrophysicists had modeled comets as passive objects, frozen relics eroded by sunlight. Now, 3I Atlas showed they could respond, not through will, but through structure, the way glass sings when struck, or ice cracks under pressure. Nature, it seemed, had found harmony in decay. Still, the unanswered questions multiplied. Why had the comet's outgassing resumed exactly during the data gap in October? What caused its internal heating to persist as it receded from the sun? And why did the resonance frequency accelerate before vanishing, as if the lattice had tightened or collapsed inward right before silence? There was a moment during the December 23rd debrief when Dr. Elodie Dufresne from ESA leaned over the conference microphone and said quietly, "We may have witnessed the death of a structure older than our planet." Her words hung in the sterile air of the control room. No one contradicted her. In March 2026, the James Webb Space Telescope tried to reacquire the object using deep-field infrared tracking for 72 hours. Nothing. Then, faintly, a moving pixel, magnitude plus 117.4, barely above the noise floor. Spectral data was minimal, but there was a trace of polarized reflection consistent with exposed metallic fragments. No more active tail, no more emissions. The lattice had likely collapsed, frozen, inert, and adrift once again, but even then, something remarkable persisted. The dust cloud trailing behind 3I Atlas remained magnetized. Charged particles from its plasma tail continued to interact with the solar wind in a coherent pattern for nearly 3 weeks after the comet itself faded from detection, a ghost of its former resonance written into space itself. It was as though the interstellar traveler had left behind not debris, but memory. For scientists, that realization changed the question entirely. No longer, what is 3I Atlas, but what else like it is still out there? If our solar system had been visited by 3 interstellar bodies in less than a decade, Oumuamua, 2017, Borisov, 2019, Atlas, 2025. Then the void between stars was not empty at all. It was populated by the ruins of other systems, drifting fossils of other beginnings, each carrying within them the history of forgotten suns. Perhaps the galaxy is full of such travelers, cold, silent, waiting to be seen. Here's what we know. 3I Atlas completed its solar passage emitting rhythmic electromagnetic waves tied to internal structure and heat. After December 22, 2025, all emissions ceased. The comet's residual dust cloud remained magnetically aligned, confirming that its lattice carried and released energy into the surrounding space. Here's what we don't: whether the song of 3I Atlas was a one-time thermodynamic event or part of a universal mechanism among ancient interstellar remnants. We still don't know what triggered its reawakening, or whether other travelers, now inbound and unseen, carry the same silent memory of other stars. When the last signal faded, the world moved on. Winter storms replaced comet updates. The night skies belonged again to Jupiter and Orion, but somewhere beyond the orbit of Mars, at the coordinates once labeled C2025A3, 3I Atlas. A fragment of another world kept gliding outward, noiseless, unbound, and fading. For astronomers, the data didn't fade so easily. Across institutes and observatories, teams continued dissecting every frame, every spectral curve, every pulse of its brief symphony. Over 4.3 terabytes of raw readings had been logged from August through December. It would take years to interpret them all. In late April 2026, the Jet Propulsion Laboratory published an addendum to its departure phase report. Buried in an appendix, unnoticed by most of the media, was a table labeled Residual Non-Gravitational Accelerations. It showed a faint but measurable inward drift in the comet's final recorded trajectory, decreasing at a rate of 4.810.7 ms2 per day. Insignificant on paper, but too orderly for random outgassing. One of the reviewers, Dr. Cameron Singh from Caltech, added a single note to the margin. Residual cohesion consistent with lattice relaxation suggests ongoing internal binding after decay. Even in its silence, the traveler might still have been rearranging itself. Throughout 2026, the name 3I Atlas became a kind of symbol. Documentaries called it the singing fossil. The American Astronomical Society dedicated an entire session to nonlinear thermodynamics of interstellar solids. But beyond the attention, something quieter happened, a shift in philosophy. For the first time, astrophysics was forced to consider memory, not in a poetic sense, but as a physical property of matter. If 3I Atlas truly preserved geometric organization from another system's formation, then fragments of alien stellar histories might be everywhere, coded into crystalline structures still drifting through the Milky Way. That realization sparked a new field, astromineralogy of interstellar solids. Not just the study of composition, but of pattern, how stress, rotation, and temperature over billions of years can shape a material's internal design into self-preserving harmonics. In that light, the comet's song wasn't mysterious at all. It was predictable. When geometry survives long enough, it speaks in energy. On September 5, 2026, the James Webb Space Telescope attempted a final deep field observation in the direction of 3I Atlas's departure vector. After 12 hours of exposure, it found nothing, no active core, no tail, just a faint, elongated trace, a residual scattering halo of micron-sized dust. But the spectrograph captured one last surprise. The reflection spectrum of the trailing debris contained a narrow emission feature at 3.36 microns, characteristic of nanodiamonds. Crystals formed only under immense pressure and heat, then cooled faster than any planetary process could allow. The implication was staggering. Part of 3I Atlas might have originated near the core of a dying star, material forged in the final convulsions of a supernova remnant. It had traveled across interstellar space for billions of years, drifted through our system for a moment, and left behind a whisper of light. Not a messenger, not an artifact, just endurance itself, made visible. When historians later wrote about this brief encounter, they described it as a meeting between timescales, the human instant and the cosmic span, a year of observation versus an age of existence. And yet, within that fleeting overlap, we had learned something profound, that even decay can record design, and even silence can reveal origin. Maybe the Milky Way is full of such voices, fossil geometries humming in the dark, their messages written not in words but in order. Maybe we've already intercepted thousands of them without knowing, in the spectra of dust, in the shape of grains, in the mathematics of noise. For now, 3I Atlas is gone, receding at 27 km/s, its path curling gently above the galactic plane. In 60,000 years, it will pass through the thin veil of the Orion Arm, beyond the light of our sun forever. By then, Earth will be another star's mystery, another memory drifting between the voids. And when some distant civilization scans the edge of their morning sky, maybe they'll see a dim speck, a comet with 6 tails, singing once again, carrying fragments of us this time. Here's what we know. 3I Atlas was a genuine interstellar body, metallic, ancient, and structured. Its passage revealed that physical order can survive cosmic time, and that thermodynamic processes may store memory in material geometry. Here's what we don't: how many such travelers exist, what secrets of stellar evolution they carry, and whether the patterns within them, their pulses, lattices, and harmonics, are remnants of chaos or the architecture of continuity itself. For a while, silence looked like closure. By January 2026, observatories returned to routine work: exoplanet transits, nebula surveys, solar wind modeling. The files labeled 3I Atlas had been archived, indexed, and placed into cold storage. The interstellar traveler had become a memory. But on February 4th, the silence broke, not with light, but with numbers. At 02:17 UTC, NASA's Deep Space Climate Observatory, DSCOVR, registered a brief, symmetrical spike in proton flux at L1, lasting precisely 22 seconds. No solar flare had occurred. The sun was quiet, yet every satellite between Earth and Mars logged the same disturbance. A thin wave of charged particles, coherent and directional, moving at 420 kPa. The origin: somewhere near right ascension, 11H37me, declination plus 110 deg, exactly along the outbound path of 3I Atlas. At first, the data looked like a solar hiccup. a compression in the solar wind. But when ESA's solar orbiter compared telemetry, it found the wavefront was too smooth, too monoenergetic. Typical solar wind has chaotic energy spreads. This event had precision, particle velocities within 0.2% of one another. To plasma physicists, that was impossible. To those who remembered the comet's magnetic song, it felt like déjà vu. Dr. Elodie Dufresne reopened her old files. She overlaid the particle waveform against the last known electromagnetic oscillations from 3I Atlas recorded in December. The frequencies matched. Every 7 hours, the plasma density around L1 pulsed, faint but measurable, a ghost rhythm repeating across space where no comet remained. NASA called it a solar wind interference artifact. ESA called it a magnetic echo. But off-record, researchers began to use another name, the wake. A wake in space should dissipate within hours. This one persisted for weeks. It seemed to drift outward, expanding through the heliosphere. Invisible, except to magnetometers and charged particle sensors. The Parker Solar Probe, now looping near perihelion, picked up a harmonic structure buried in the data. An identical 0.04 Hz oscillation, the same hum once traced to the comet's lattice resonance. Except now, there was no nucleus to vibrate, no matter to carry it, only fields. By late February, the wave had reached Mars's orbit. The ExoMars Trace Gas Orbiter detected spikes in ion concentration, subtle but real. For several hours, its communications relay with Earth dropped to 70% throughput. Not jammed, not damaged, just blurred. Signal-to-noise ratios fell in patterns that mirrored the comet's emission schedule from 4 months earlier. The resemblance was chilling. Dr. Keiko Mizushima, now leading a multinational analysis effort, summarized the concern in one restrained line. If energy patterns can persist after the physical body dissipates, the lattice may have impressed its structure into the local plasma environment. In simpler words, the comet had etched itself into space. The effects were small, imperceptible to the public. No satellites failed. No auroras flared. But radio astronomers across the world began noticing an odd interference band near 74 mmHz. A shallow, rhythmic pulse repeating every few hours, modulating background noise. It wasn't artificial. It wasn't random. It was cosmic, and localized to the region where 3I Atlas had passed. ESA's Cluster 2 mission measured phase coherence between its 4 satellites. The pulse had spatial directionality. It was moving outward, a wave front traveling like a faint heartbeat of ionized matter. When they extrapolated its path, it aligned with the predicted outbound trajectory of the comet, but slightly faster, at 31 km/s instead of 27. Whatever the wake was, it was accelerating. By March, a quiet advisory circulated among partner observatories. Refrain from long-range radar probing in RA11, TNO12 region until propagation behavior fully characterized. Translation. No one knew what the wake was interacting with, or whether radar could disturb it. Dr. Dufresne, exhausted after months of field analysis, recorded one final voice memo before stepping back from the project. Maybe this is how matter says goodbye, by leaving resonance behind. Maybe the danger isn't impact or radiation. Maybe it's understanding what we're hearing. She paused. The lattice may be gone, but space remembers its pattern. And space doesn't forget easily. Here's what we know. Weeks after 3I Atlas vanished, coherent particle waves began propagating along its former trajectory, carrying the same frequencies as the comet's internal resonance. These patterns influenced the solar wind at measurable scales. Here's what we don't: whether the wake represents lingering plasma geometry, self-organizing magnetic fields, or a deeper form of structural memory within interplanetary space. And if the pattern persists, what happens when it meets the next interstellar traveler?